everyone. This class now, if we look at the calendar, this is now entering week number 4. Okay, week number 4. And you can see a whiteboard here. I'm just going to recap what we have covered in the past classes. See, so what we have done is we have done an introduction. Introduction.
You are not
Yes.
sharing your screen.
Oh, I'm not sharing my screen. Oh, yeah. Thank you for okay. Thank you. Okay. Thank you for telling me, or else I'll be talking alone. Where's the mouse? Okay. All right. We have done introduction, and in introduction we have covered. You have completed successfully completed your assignment. Okay, your assignment 1. I think there are still people who have not submitted. Assignment 1 you have done. You have taken pictures. Okay, you have taken pictures. So you have actually seen now real structures of steel design, steel structures, and you have seen the connections. Okay. Now the next thing is you have successfully done section classification. Section classification based on table 5.1. Okay, table 5.1 of the Eurocode 1-1. And after that, what have we done? We have finished this. We have gone into truss. Okay, we have done truss design. That's the first, and this is the second. Inside truss design, you have already know how to do distribution of loading. Let's change the pen color. We have done the distribution of loading from here to here, on slope, on plane, and so on, vice versa. And you now you know how to. If this is how it is, you know how to calculate the internal member force for all this, so on. And you know how to find whatever sizes or sections that you want. Okay, that's what you have done. Then the next thing is the purlin. The purlins. Okay, you already know how to design the purlin. There are 2 methods that you could use, either the beam method or the empirical method. Empirical method using 5950 BS 5950 table 27. And you know what are the criteria, the restrictions or limitations in using this empirical method. All right. And I have given you some work to do on this CQI number 1. CQI number 1. And the due date is on the 30th of the 4th. This week, we are going to cover beam design. And this is a rather slightly longer chapter, which will take like 2 weeks plus a bit. Okay, 2 weeks plus a bit to dwell on this. Okay, in beam design, let me get another page. So in beam design is divided into restraint beam and unrestrained. So I'll give you the big picture first. Okay, restrained and unrestrained beam. Of course, in beam design, what we need to do is beam design So the process here is we have to check on the loads. Okay, you get the loads, load distribution, get the load combination, the load distribution. Then we have to select size, estimate. Or select size. So if you want UB, you're going to see what size you want. How do we do it? We're going to see later in the work example. And then once we've got the size, under ULS, we have to check the shear and we have to check the bending moment. Okay. And if it is unrestrained beam, it involves lateral stability check. Then under SLS, we have deflection. If it is a very long span beam, say like 8 meter, 10 meter and above, we have to check in terms of vibration. Okay, vibration towards the floor, felt vibration. So that's what in terms of the chronology of it. Okay, now what is then restrained and unrestrained beam? If I draw here, the red one are the, well, let's call it the beams, okay? And the green one is the column. Okay, the green one is the column. So what we have here now is we have a panel. That's a panel. So if this panel is a reinforced concrete slab, goes on the top. What it does is that it will prevent the beam, the red color beam, from going outward. So if I draw the let's erase this off. Oops. So what we have, this is the Y direction, and then this is the X direction, and this is the Z direction. Now this one is going out on the Z direction. Okay, going out on the Z direction. That means it is out of plane. Out of plane. So if it is restrained, then this out of plane does not happen, okay, in a fully restrained beam. But what can happen is, I put orange color, it will deflect downward, and this would be in the negative Y direction. And this is called in plane. It's called in plane. Now let's look on the other side, on the right side, what we have here. Slam a bit more. So again, this. And this time now, there's no slab on the top. So there's no slab on the top. What's going to happen is it's going to deflect outward. This is Z direction, and it's also going to deflect downward. And this is the negative Y direction. So in an unrestrained beam, there is no slab on the top holding the upper part. So what do you mean by upper part? Upper part, if I need to come down a bit, slide it a bit more. Get a bit more space. So you have so if I draw so what we have here is we have the upper flange. That's the upper flange. And down here, that's the lower flange. Okay, the lower flange. So the upper flange is the compression flange, and the lower flange is the tension flange. So the upper flange in an unrestrained beam, that upper flange, which is under compression, will tend to be able to move to the right or to the left out of plane. And it's going to twist. So you can see here, it's a bit twisted. Twist. All right. So the upper flange is going to go laterally to the left or to the right, and it's going to have a twist. So this movement is called LTB, lateral torsional buckling. So in this case, we need to check the lateral torsional buckling capacity or resistance that is inherent in the beam. Now, there is also another possibility where this would happen if there is a slab. If there is a slab, but it is not fully locked into the beam. So it can also create an unrestrained beam scenario. Okay, so this week we will cover this restrained beam. Okay, maybe on Wednesday we can do a bit more something else on the unrestrained. Okay, let's see. We move on to the next slide here. Okay, load distribution. Outline of this lecture, load distribution. How do we distribute the loads? If you have that's the beam, and then there is this slab that's inside. How do you distribute this to here and here and here and here? How do you do that? Who knows? Gets a bonus. Nobody wants to try? What document do you refer to? What do you call names? Lo Kang Chia. Hello. Where are you?
Try using Ly for FX.
Who is that?
Kang Jia. No.
Okay. All right. Say again.
We're going to check using Ly for LX. If it's less than 2.0, then it is a two-way slab.
And okay, if it's two-way, if it's two-way slab, then what do you do?
Then need to return to one table to check the loading, to get the factor and transfer the loading to the bin.
Or what is that table? And where do you find that table?
In Eurocode 2, I guess.
In Eurocode 2, there's no table like this. Don't have. It's in another standard. What is that standard? What is that code? Can you tell me that code? Kang Chia?
VS
BS
8110.
8110.
Okay. All right. Yuling also answered. BS8110. Wait, I give Kang Chia the bonus first. Okay, Yuling. Where in BS8110? What is this table?
Is
VX beta VY.
is table 3.14 and 3.15.
Okay,
For bending moment is 3.14.
315. Okay, table 315. Okay, so it's this table. So everybody needs to know and recall back this table here in how to use it. So you've got to have this here and here. Okay, this one is important. All right, if you want to see it's let's see if I have it here. No, don't have it. I didn't open this morning. I opened it up. Okay, you've got that table. You need to have this table. Another one, there's another method. You either use the area method. If you have the module, okay, the module has a table. It provides all this area. Either you have triangle or you have trapezoidal. Okay, you should have covered this during RC design. Okay, then there's another method. That's the empirical formula. Empirical formula is like this. You have for this one NLX over 3 W equivalent. Then you have another one for the trapezoid, W equivalent NLX over 6 times 3 minus LX over LY squared. So this is only correct for all adjacent sides are continuous. Okay, all sides are continuous. Other than that, if you use this one, then it's not accurate. Okay, so this is the load distribution part which you need to know, because when we design the beams, when we design this beam, for example, we need to find out what are the loads coming from the slab. So in this outline, in this lecture, we have also restraint beam. So we will cover for today, we will want to cover this part here. Okay, mainly on this one. Then this one will be the next classes. We've got this one. And then one-way slab. Examples of one-way slab. You've got precast units, slabs on here. What are the example of precast unit slabs sitting on the top? Who can give me examples of it? Who can give me examples of precast unit slabs? Nobody? In this one, who is this? Aisha Hanan. Aisha Hanan.
Yes, doctor.
Yeah. What are the examples of precast unit slabs that you can put the one like the one I draw on the red color?
Precast.
You wanna pass? Yeah.
no.
What is that?
Precast concrete.
Yeah, but what are the product name? What's the product name? Anyone else want to try? Rasha, you know? You don't know?
I don't know. Don't
You
know.
don't
Sir.
Okay. All right, Sadesh, Holocaust slab. Okay, good. Sadesh, can you find a picture of it and share with the class? Sadesh.
Yes, doctor.
Yeah, you want to share with the class your picture? Sadesh says it's the Holocaust unit slab. Okay, let's see. S. Sadesh. Picture?
Do I need to share the screen or can I send?
Yes, you need to share the screen. You don't share the screen, the rest of it can't see.
Okay.
You find under Hume also can. You find Hume. Somebody can find Hume while Sadesh finds a picture. So somebody finds from Hume.
Can see my screen, doctor.
Coming, it's coming. All right, good. That's the one. Okay. Yeah. So you can see here, there is the Holocaust unit that you can put it directly on top of the panel. Okay, on the panel. All right, thank you, Sadesh.
All right, doctor.
Yeah. Now, in for example, in the manufacturer Hume, they have the. Oh, I have a phone coming in. Just a minute. You want to pause the recording? Okay, yeah, you can resume that recording. Sorry about that. Must be a wrong number. I'm not expecting any call. Okay, now if you look at the screen here, we have, you can put a Holocaust slab unit in, and its thickness, say 125, okay, 125, and span can be, it can be 4 meter, can be 6 meter, can be 8 meter, all right, depending on what's this. Okay, if this is 6 meter, then it will be 6 meter. And now, then they will put a grouting to lock here. Okay, they'll put a grouting to lock here with steel bar. Okay, so how do you transfer the loads? It does not normally become like this. Okay, you have normally you have this. You know, you can just draw it out. Okay, WL square over 8, WL over 2, and so on. Now, normally it's not always like this. Sometimes you get cases like this. So in cases like this, then you have to do it manually and calculate all this. Okay, so in exams, don't expect it to be straightforward like this. Okay, in the cases when it is like this here, then you have to know what to do and how to do. Sometimes you can use tables. Let me find, I have it. Let me find examples of where do you find so you can use tables like this, documents like this, where you can then say, for example, if you have okay, simply supported 2-point loads. I mean, this one you can memorize it. But if it is like this, okay, or if it is indeterminate two-span, where do we go? If it is two-span, then you can have it like this. Okay, you can find your reactions, and you can find the maximum moment, hogging moment, and sagging moment. Straight away use these formulas, and your deflection. Okay, tables like this are very useful for you to learn how to use them. Then we come back to, where's the PowerPoint? Come back to this one. Okay, steel beam construction. There's two I have explained. Laterally restrained beam. That's what we want to cover today. So in laterally restrained beam, how do we define it? Okay, how do we define? Restrained beams are beams that do not fail by lateral instability. The word lateral refers to horizontal. Okay, horizontal, it goes out. I've drawn this before. If it's like this, let's erase it. So if you have it like this, okay, now we have this, and this compression flange. Where's the compression flange? This one, the top one is the compression flange. If it is not, if it is unrestrained, then this one will have the tendency of going left and right. That's the lateral transverse movement, instability. So the compression flange in a restrained beam is held. So you have a slab on the top, thick slab on the top that holds it. So then, therefore, this red color flange, this red color compression flange is held. Okay, dipegang is held. It cannot move left and right. And then you have resistance to lateral torsional buckling. So it does not, this whole thing does not go on an S formation. It does not twist and buckle because of the blue color slab that is holding it at the top. Okay. So in this case, we call it as a restraint beam. And in the restraint beam, what do we have to check? Lateral restraint force. That is then we have this, the loading, that's the load. Then we have the bending and the shear check capacity. And then we have the web bearing and buckling. This one is the next. I've uploaded two slides, A and B. So B is this one, okay? What is this? This is the definition given by 5950 British Standard, clause 4.2.2 about what is a restraint beam. Okay, a full restraint exists if frictional or other positive connection of a floor to the compression flange. Okay, restraining the compression flange is capable of resisting a lateral force of 2.5% of the maximum force in the compression flange of the member. So examples of full restraint, cast in situ. Okay, we just pour we can pour, if this is, you see the picture on the top, you pour the concrete on the upper side. Okay, there's a cast in situ. Precast, we've talked about it just now. Steel plate flooring, welded or bolted with close spacing. It must be close spacing, and the size. Okay, the size. If it is a small screw or very distant, okay, very distant spacing, then we cannot consider it as restraint. If it is just timber flooring with small connector, then it will be unrestrained. And we are bracing elements closely. Space. So these are the schematic diagrams. Okay, schematic diagrams of the of a restraint beam. So what do we have to check? We have to look at all this. You need to turn to your clause Eurocode. These are the clauses that you need to start to turn to. So we will need to look at the example afterwards. So if you see here, shear resistance, open up to this clause, 626. No, Akila. No,
Yes,
Akila.
doctor.
What page is this, 626?
Wait.
So if you look here, you tell me when you're ready. If you look on this slide here, you have on the left side, this inequality. This, when you see this sign, this is an inequality. On the left side is the demand. The demand comes due to load and cause an effect. The effect here is a shear effect. So how do you get this? If you have a simple one, is like this, and then you've got the shear force at the end span. So that's your VED, okay, which is calculated WL over 2. All right, there's no. So you've got this demand on the left side, and the right side is your resistance. That's your resistance. So that's the capacity. The resistance can be calculated in this formula. Are you ready, Akila? No, Akila.
Doctor,
Yeah.
is the clause is in Eurocode?
Yes, has to be in Eurocode. We are talking about Eurocode. Yeah.
I don't have the Eurocode.
How
If
come you
Eurocode 3,
Eurocode 3, yes.
71.
Page 71. No, it's not page 71. The physical book.
Yeah, physical book.
The physical book. Eurocode. Clause 6.2.6.
Yes.
6.2.6. What does it write there?
Design resistance of basic components.
Design resistance of basic components. No. No. The page
Page
6.2.6.
50.
What does it write there?
Page 50.
Yeah, it's page 50. Saibal. How do you pronounce your name?
Sylvie, doctor.
Sylvie. Okay, Sylvie. All right. It's where is it? Akila. I
Doctor?
don't know which one you are referring to. Okay. You got to refer to Eurocode 3 1-1. Okay, Eurocode 3 1-1.
Okay. I'm sorry.
Yeah. So page 50. I'm not sure. Well, you tell me you don't have this document, then I'm not sure how you do your section classification the last in the assignment one. Okay, it's page 50. Okay. In page 50, so in page 50, you will find this equation. So please highlight this equation. And it is, if you do 1 divided by square root 3, you will get 0.6. So that's what I've written here, 0.6. So if you look at this, there's this A of V, AV. So what is AV? What is AV? Siti Nur Amani.
Shear area.
Shear area. Okay. How do we get this shear area? Refer to the code of practice. Where is it written for to calculate the shear area? What's the form? Where the formulas are given? Where are the formulas given? Amani. Shear area.
Dekat page 51 ke?
What does it write there? (51) tulis apa? What is it written there?
The shear area may be taken as follow.
Okay, good. There's A, B, all the way until G. Okay. Now, it all depends what section you are using. Are you using a UB, a row section, such as the I type, whether I tinggi ke I rendah? So this is a UB and this is a UC, or are you using a rectangular hollow section, or are you using a circular hollow section? So all there is given, the AV, we have to calculate the AV, because the shear depends on the area of shear, the effective area for shear. Then you can calculate the resistance. These are the resistance. Okay. Now there's another one here which we will talk about. I will explain later. There's this thing here, shear buckling resistance. The shear area is in effect the shear of the cross section that can be mobilized to resist the design shear force. The design shear force is your demand. So this shear area, the ones in blue, is blue. Okay, that's your shear area. That's the calculation. So we need to identify what is this shear area and to calculate how much. Now, what happens if your shear area is insufficient, and also if your H over T, that's the web, okay, is insufficient. Okay, if your H over here, if your shear buckling, if it's H over T is more than 72. Okay, if it's more than 72, what it means is this. Take a look. H over T. That means it's very high. That's your H. Very high. Now, HW is actually after the radius. And then this one is the radius. So H over W is actually here, to be exact. If it is very high, divided by very thin web. So you get more than 72. Okay, more than 72. Okay, you go to page 52. You go to page 52. Are you all looking? So if it is more than this, then you need stiffener. If you don't provide stiffener, then this is what, or you don't provide enough stiffener, this is what's going to happen. What's going to happen is white color, is this folding effect. See this folding effect? Okay, so this is called buckling of shear buckling in a thin web. What is the stiffener? The stiffener is this. That's the stiffener. So you put the stiffener here. Because the beam, the I-beam is very high, very tall. So therefore we need to strengthen the web so that it doesn't go like this. So if you put the left and the right with the blue, that's called the stiffener. This is a stiffener. Then the green effect will not happen. The folding effect will not happen. Okay, the next thing is the bending resistance. That's the bending resistance. Where is this? Clause 6.2.5. Clause 6.2.5, Muhammad Izzat Nakiuddin.
Yes, sir.
Okay, where is this? What page? 6.2.5. Now, semua formula yang saya bawa perkenalkan kat sini, please go and highlight in your Eurocode, okay? The one that you have printed out.
Page 50.
Okay, page 50. All right. So you have here W P L F Y over gamma M. The birth of this, or how do you get this, is actually it's actually like this. Stress, bending stress equal to My over I, which is M over Z. Z is the section modulus. So if we rearrange this one, yang ini, this one we use the notation Fy, and this one we use a notation WPL So we rearrange this, we can rewrite it to become M equal WPL times by Fy. That's the same one on the top, and divide by gamma M. So that's how it is. So if you look at this one, what you have, this is the resistance. And on the left side is the demand. How do you get the demand? The demand comes from the load. So here you have this UDL load. That's the W load demand. And the load demand creates the effect of a bending moment, which is M equals to WL squared over 8 in this case. Okay? So you need to compare the left side, with the right side. The demand must be less than the resistance. So if we write it in ratio dalam nisbah, MED divided by MCRD must be less than 1.0. Okay. So let's look at the work example. Okay, we look at the work example. Here in the work example, we've got a frame. So if you look at here, what's the span of this beam on level 1? Muhammad Haris.
Yes, doctor.
What is the span?
Wait,
Wait for what? Why wait? Tidur ke? On the screen. On the screen. Tengok screen. Aduh. Tengok screen. Jawapan kat screen tu. What is the span?
8 meter.
8 meter, yes.
Yes.
Okay, it's 8 meter. See 8 meter on the top here, 8 meter. Okay, we're going to design this beam here. Okay. Now, then you look at the floor plan. Just now cross section. So you look at a floor plan. Okay, if you look at a floor plan, Aliyah Izzati. Nur Aliyah Izzati.
Yes, doctor.
Okay, what grid line is the beam that we are going to design for?
Beam G122.
Okay, G/1-2. That's the grid line of the beam. That's the address. Okay, dia punya alamat tu beam tu. Okay, now if you look here, now we're thinking of load distribution. Okay, you got a load distribution onto this G1/1-2. What is the tributary width of this beam? Going to ask siapa tadi? Nur Akila binti Misron.
Yes, doctor.
Yeah. What is the tributary width?
6 meter.
6 meter. Okay, very good. I give you a bonus. 6 meter. Mana nama kamu ni? Oh, here. So 6 meter. Now look carefully. How do we get 6 meter? You see the loading, the load is going to go half to this side. And then another half to this side. Therefore, now this is 6 meter. This is what we call tributary width. So if we have a unit, the loading comes with area load, kilonewton per meter square, ataupun kita panggil KPA, kilopascal square. You multiply with the tributary width, which is in meter, you will get kilonewton per meter. That's the load if we draw this one out. If we take this, if we take this beam, so we're going to take this beam out, and that's what you're going to get. Ini. Okay, ini ialah 8 meter. Now you understand how to do. So if you are designing for this beam, what is the tributary width? Zafri bin Ayub. Zafri bin Ayub. Where are you? Is this person here? Yeah, he's here in the class. Zafri bin Ayub. 3 meter. Okay. Very good. Mike tak ada ke? Di mana kamu berada? Where you? Zafri. Rosa, doctor, where are you? Physically di mana? Yalah, my home, betul. Lokasinya? Oh, Simpang Renggam. Okay. Alright, now this beam, rentang dia 6 meter. What is the QK? What is the load on this beam? This beam carries what load only? Let's ask
Slab.
Harith Iskandar.
Yes, betul.
Carry apa load?
Slab.
Slab. Ada carry slab tak?
Ni secondary beam.
Dia carry
Secondary
beam. Yes. So kalau lukis yang merah ni, free body diagram, dia nampak macam mana?
Ada point load dekat tengah.
Okay, ada point load. Ada UDL tak ini?
Sekejap. Memang tak ada slab kan? Kalau tak ada slab, tak ada UDL lah.
Tak ada UDL. Okay, dia hanya carry secondary beam. Slab tu hantar kepada secondary beam keluar satu point load kat beam ni. So dia keluar macam ni. Okay, so this is when we look at the study, the plan, the drawing, kita kena tengok secara keseluruhan. Now then there's another one. Wait, siapa cakap tadi Harith, is it?
Yes, betul. Haris Iskandar.
Lupa nanti bagi bonus. Okay, now there's another one. This one. Ini restrained beam ke unrestrained beam? Let's ask Chong. There are two Chongs here. Chong Chun Yuan.
Yes, doctor.
That beam, is it a restrained beam or unrestrained beam?
Restraint.
Which beam are you talking about? Mr. Chong,
Yeah.
which beam are you talking about?
The purple color one.
The purple color one. Okay, this one. Restrained beam or unrestrained beam?
Restraint.
Restrained. You sure?
Not sure.
Not sure. Okay, why you say it's restrained? No answer.
Sorry, sir. I don't know.
You don't know. Okay, let's ask another Chong. Chong Hui Ling.
Yes, doctor.
What's your answer?
For the purple color beam.
Yes. Restrained or unrestrained? What makes it restrained? Huh?
Such an independent beam.
What independent beam? What's your answer?
For the purple, I think it's not restrained beam.
Unrestrained. Why you say it's unrestrained? Come on, quickly. Why you say it's unrestrained?
Because it's for staircase.
Okay, what makes a particular beam restrained? What makes it restrained? What makes it restrained? Just now I explained so much.
The presence of slab.
The presence of slab. Yes, the presence of slab restrain what? Restrain what of the beam?
Lateral movement.
Yeah, restrain the lateral movement. It holds on to what? What does it hold on to? What does the slab hold?
Compression.
Yeah, the compression what?
Flange.
Yeah, the compression flange. Okay, good. Wait, I'm gonna give bonus to these guys, Lo and Harith. Lo, you are all listening. The rest are not listening properly. Lo. Where is Lo? Lo and Harith. Both of you got double bonus today. Okay, so you see, just now I explained so much. I said to you all, I'm gonna draw it. This one and this one. This top one is a compression flange. So you put a slab on the top. Okay, you put a slab on the top. You either tie it in or you grout it in, and it holds this from moving laterally to the left or to the right. That's top one is called compression flange. Okay, now I'm gonna ask, what's the name of the girl? Chong Hui Ling. Why you say this is unrestrained beam? I want to give you a bonus. You tell me the correct answer. Why you say this purple beam, which is on the far right, is an unrestrained beam? Quickly.
The compression front.
You see here, this is a slab. Look here. Tell me why. Your answer is correct, but I need to know why. You cannot simply guess.
How to say?
How to say? Say lah. Just say it.
There is no slab
There is no slab. Why is it no slab?
because there's for the staircase.
Very good. That's a stairwell. There's no slab there. That's why this one is an unrestrained beam. Just as simple as that. Okay?
Okay.
All right. Why you think so complicated? Okay, Chong Hui Ling, you get a bonus.
Thank you,
Okay.
doctor.
All right, let's move on. So, okay, let's look at the example calculation. The example calculation is here. Now, what is the time now? 12:10. What time we supposed to finish?
1 p.m.
1 p.m. Okay, don't sleep, huh? Don't sleep, huh? Anytime I'm going to call anyone. Okay? Okay, now, you look at this example. You've got the loads. Let's use blue. Okay, you've got this. These loads are all in KPA. That's a GK. Now I'll leave you to read yourself, okay? You got to read how to get all this, huh? Okay, because in the exam, if you are serious, you want to pass, and not just pass, you want to do well, then you need to read. Okay, if you don't understand, then you can come and ask me. Right? So you got GK, QK, and they are in KPA. So once you get the KPA, you go down, go all the way down. That's the one. It's in KPA. So the beam is 8 meter. Bay width, which is also the tributary width, 6 meter. And then we do the load factorization. So in this case, they use this equation from Eurocode 0. They have this reduction factor. You don't want to use, it's fine. You just go with this and with this, 13515. So you get, assuming this is what it is, so it's 60 kilonewton per meter. So you have got it in KPA, multiply with the tributary width, you get it in kilonewton per meter run. Okay, this is then the line load. From the line load, you can calculate. So what you get here is your beam with a line load of 60 kilonewton. That's your design load. That's a factored design load. And you can then calculate the MX, which is 478 kilonewton meter, and the maximum design shear, maximum shear demand is 239 kilonewton. So how do you then begin your work? You begin your work by making an estimation of what size. What size? You cannot just flip your finger on the section properties and take on any size. There's no such thing. Okay, there must be a guide towards finding the size that is closest to the best. So how do you do it? You come with the formula. Remember the formula, M moment equals to WPL. What's WPL? Let's ask again. Mr. Get a Mr. Ilham. Ilham. Inspiration. Ilham. Mana engkau? Ilham di mana?
Yes, Doctor.
Ilham Shafil. What is WPL? Baru nak cari.
Plastic modulus section.
Okay, plastic section modulus. Very good. Do you know where to find it in, if I give you a section size, do you know where to find it? Tahu mana? Tahu ke tak tahu?
Table of property.
Dekat belakang buku.
Ya, belakang buku. Okay, let's start with this. Saya bagi size ini. Okay, carikan. Apa dia punya WPL dia. Okay ya, cari ya, nanti tunjukkan. Snapshot. Letak jari kat sana, snapshot ataupun pen kat sana, snapshot dan hantar bagi saya tengok. Boleh?
Okay.
Okay, alright. So we have this WPL, which is the plastic section modulus, Fy, and you have this. So now rearrange this one. Rearrange this because we want to find what is WPL. That is the geometry size that is inside this formula. So we have your M divided by Fy. Okay, divided by Fy. And then you've got gamma MO which is 0, which is 1. So solve this, which is this. Then you have the section modulus required. This is the required. So you're going to find from the table of section properties what size you want. First of all, what section? You decide what section. What section? You like a UB, or you like a UC, or you like a RHS? You decide. So in this case, it's a UB. Okay, UB. And also you got to decide what grade you want to use. This case is a S275. And then you decide what thickness you want. Do you want less than 40? So if you want less than 40 mm, then this is your grade strength. Okay, this is your U strength, 275. Okay, so he has sent to me. Let me have a look. All right, very good.
Doktor,
Okay.
doktor, nak tanya
Yes.
boleh?
Apa dia tanya? Boleh tanya.
Yang section modul WPL ni lah reference kita untuk tahu size lah daripada kita tengok dekat table ni lah.
Ya, betul.
So
Ini
kita fokus dekat WPL section modulus, plastik modulus ni.
plastik. Kita nak, okay.
Required lah.
Yes, kita selalu nak guna plastic section lah. Okay, target ialah kita nak guna plastic section. Now, we can go either class 1 or class 2 lah, compact lah. Okay, that's why kita akan guna WPL ni.
Okay, doktor.
Okay, alright.
Okay.
Now, we use this formula. This is the formula to determine as at the first entry point. Entry level determine the size. Okay, so we use this formula. This formula is based on strength. Okay, it's based on strength. There's another formula or another approach to decide the size. Another formula to decide the size, another approach to decide the size is based on deformation. Deformation. Okay, just now strength is based on ULS. ULS, so we use this formula. Another way is we use deformation SLS. So we have, if for example, if it's a UDL simply supported, we have that delta equals to 5W. This is a little w, the load L kuasa 4, 384 EI. Okay, 384 EI. Jadikan I, make I as the title. So I as the title, and then we find what is this I required, and we get the size. Okay, this is another approach. So delta here, what we use, we can use span over 360. Okay, so this there are two approach. Sama ada kamu guna approach strength ULS ataupun you guna approach deformation SLS. Okay, untuk cari size permulaan. Okay, bukan size itu jatuh daripada langit, tidak. Okay, alright. So let's see. Once we get the size, so this is the size. The WPL provided, this is the provided one. Okay, now once we get this size, this is the provided one, which is larger than this 1738. Now we need to check. What do we need to check? We need to check everything. We need to check shear, we need to check bending, and then we need to check deflection. But before all this, we need to see whether what class is this. Confirm the class. Confirm the class. So it's got to be class 1. So we do the section classification. Now, all this, when you do the question answering as far as the context of academic test exam, tak payah tulis lah ni semua. Tak payah tulis, tak ada masa. Okay, no need to write out all this. So then you find, so again, this one no need to go and count. You just go and do this one. Okay, find from the table. You find all this from the table and you get class 1. So this is class 1. So now we check the shear. When we check the shear, so we check the shear resistance. Check the shear resistance. Remember this one, 626. 626. Just now, yang hantar saya tu siapa? I write down the bonus. Ilham, is it?
Ya, doktor.
Ilham, okay. Siapa lagi tadi ada sepatutnya dapat? I got write down already. Okay. Alright. So, okay, shear resistance. So that's the formula. First thing to do, we need to calculate what is your AV. What is AV? Kita tanya Nazifa. Asfa Nazifa.
Yes, doctor.
Okay, what is AV?
AV is area.
What area? What is this area?
Shear area.
Shear area, okay. Where do we get the formula shear area for a UB roll section? Where do we get the formula to calculate shear area for a UB roll section? Roll section. Mana nak cari formula ni?
Dekat page 51.
51. Di atas ke di bawah ke di tengah?
Di atas.
Di atas. Okay. Everybody please highlight all this. Okay, highlight all this. So I give you a bonus. Okay. So now.
Thank you, doctor.
You're welcome. So we calculate all this. Now, when we look at all this, it looks quite straightforward, easy, but I encourage you to do it. Okay, you kena buat sendiri buat Kalau tak buat nanti tak nampak. Nampak senang lah, memang is straight direct. So, but you have to calculate and do it. Okay, so then we go down. We calculate the VCR. Okay, so once you get the AV, you put it into the formula, which is 0.6 FYAV divided by gamma MO, which is this one is 1 divided by square root 3 is actually 0.6 lah. Okay, so you get it 756. Now take note, the demand is 239. The resistance is 756. Do you not think it's a bit too over?
Yes, doctor.
It is a bit too over, but there is a reason for it. There's a reason for it to be too over. Now, we do not want the shear. Do not want the shear shear, how do I say it? The shear ratio. The shear ratio, the ratio for shear, shear ratio, this shear ratio, this shear ratio, we are talking about this shear ratio. We do not want this lebih daripada 0.5. We don't want it over 0.5. We are not over designing. This is not over design. There's a reason for it. We don't want it to be over 0.5. Why? Because when it is more than 0.5 ratio, it is going to affect the moment resistance. It is going to affect the moment resistance and bring it down. So this is called shear effect on the moment resistance. Okay, this is written in the code of practice. If you look at, where is this? Page 53. Page 53, 6.2.8, number 1 and number 2. Number 1, number 2, number 3. Okay? So remember this. So there is a reason for it to be this small. So next time when you do design, you make sure that this ratio is less than 0.5. Okay, the ratio is less than 0.5. Now, we move on. Okay, after we check the shear capacity, we need to check the shear buckling. The reason for checking this shear buckling is that we do not want, we try our best to be economical. Now, the depth now is a 457. This depth is a 457. We know that if it is too deep, whereby the ratio of H over P of the web, okay, if it is larger than 72 epsilon nu, okay, if it is larger, if this is correct, then you need to provide, then you need to do a design of stiffener, because the web is going to buckle. So we don't want this to happen. We do not want to have an extra fast stiffener on the web. If you need to have an extra stiffener, if these comply, then you got to go to 1-5 of the Eurocode BSEN 1-5 to do the design of the stiffener. But we don't want to have this. So when we do not want to have this, what we must do is that we must make sure that this condition applies. H over TW less than 72. So we check here, and is 43 less than 72, and this epsilon, nu is 1, okay? And this epsilon is the same one as in the table for section classification, okay? So 66, we've got 66, so therefore shear buckling check need not be considered. So you do not need to have the stiffener. Lastly, we check the moment resistance. Moment resistance, again, we use back the same formula and we get this. This is a nice design. See? 0.95. So a good design, not too over, okay? Not too over, is somewhere between 0.8 to 0.9. A bit plus, as long as it's below 1. Okay, the ratio, I'm talking about the ratio. So if you get something, a moment design demand where you get the ratio of 0.3 or 0.4, what is telling you your size is too big. Okay, so we go down. Now all this I've explained just now regarding the 0.5 of the shear. So lastly, we have this service limit state to check the deflection. So in deflection, we have G plus Q. Okay, but when we use this, with the assumption that this is derived based on Q only, and that the original load is already, the dead load is already sustained there. So we use Q without factor, no factor. So there's no factor. This Q here, there's no factor. So finally, we get this. The demand or the actual deflection is less than the criteria, and the criterion, the limiting deflection. So therefore, we can adopt this. Okay, so this is finished now. So now you can design a restraint beam. So you can stop the recording now. Any question? Yes, we mean. No, not simply choose. The size not I won't say simply choose. We use this. Use this guideline. Okay? Use this based on strength. All right, so it's not simply choose. You use that as a guideline.
Doktor nak explanation sikit lah. Yang dekat WPL kan, apa plastic modulus, kenapa kita kena tengok Y axis berbanding Z axis?
Major axis.
Oh, sebab
major axis. Y axis is major axis. In steel, Eurocode 3, Y axis is major axis. Now always remember, I major is always bigger than I minor. Jadi sama juga Z. Now saya suka because I old school lah, British standard. Okay, I like to use the old convention, old sign notation. Z major always bigger, selalu akan lebih daripada Z minor. So what is Z? Section modulus lah. Okay, section modulus, elastic section modulus, or plastic section modulus is S. S major lebih daripada S minor. So these are the sign convention that we use in the British standard days apply last time. Okay, so always ingat, kita beam kalau saya guna maybe you want to record, you want to add on this one in the recording. Where is our friend Wei Wen?
Wait, doctor.
Yeah. Is it recording now?
Wait, because there's an error.
Oh, there's an error. Okay.
Okay, I'm starting right now.
Yeah. Okay, can I go?
Yes.
All right. Okay, now there's a question here. Can we simply just choose a size? Or why do we, there's another question is, why do we use Y-axis and not Z-axis? Okay, so here to answer the first question is this. We cannot simply choose a size. It's not about simply choose a size. We have to use the guideline. This is the guideline which I've explained earlier on. Okay, that this is based on strength approach. Based on strength approach, we use this formula: moment equals to W PL times by Fy divided by gamma MO. WPL is your plastic section modulus. Okay, actually it comes back from this stress equals to bending stress equals to My over I, okay, which is M over Z. You rearrange all this and make Z, which is the section modulus, the title. Okay, so here we use this in terms of Eurocode standard, we use this sign notation formula. So not simply choose a size from nowhere. We use this formula as a head start to decide what is the starting size. Okay, and then we get what we call it the section modulus that is required. We go to the table of section properties. On top of our head, first of all, you need to decide, do you want to use a UB section, UC section, or any other section like RHS, or any section that is suitable as a beam member? Okay, then what is the grade that you want? What grade you want? S275, S355, you decide. As a designer, you decide. And what thickness, at the back of your mind, you decide, do you want to use something very thick or just under 40 mm? Then you can decide what is your use strength, and then plug and plug it into your formula, and you can calculate your required plastic section modulus. And then you go to your table of section properties and look which size comply or fulfill the required, must be larger than the required. So then here, that's what you get, the provided section modulus. Okay, now which axis to use? Minor axis or major axis? Is it now in Eurocode 3, major axis, always remember major axis is Y. Y is major. Minor is Z. Now this one differ from Eurocode 2. So don't get confused. Okay, don't get confused. This is different from Eurocode 2. And it's also different from British Standard. So as far as Eurocode 3 is concerned, for structural steel design, the major axis is given Y as the sign convention. And the minor axis is given Z, little z, as the sign convention. Okay. All right, why do we use a major, not the minor? Always remember, I major is larger than I minor. Z major, this is the old school way from British Standard. Z major is section modulus, elastic section modulus. Z major is always larger than Z minor. S, capital S, plastic section modulus is always larger than minor axis. So when we put a beam, when we build a beam, the clever way to build a beam, if I take it as a rectangular section, the clever way is this, like this. The not clever way, in purple, which I will draw, is like this. The not clever way of putting a beam is putting it flat. So this is called flat-wise. And the red one is called edge-wise. So the clever way is putting it the edge-wise. When you do it the edge-wise, then you are going to use all that is of the major here. Okay, all that is of the major. So why, if you look at it like this, that's your major. Okay, and this will be your minor. So if you want to put it in the context of a steel. So steel, UB section. UB section, then we draw it. I'm trying to choose a pen color so you don't mix up all. So it's going to be like this. Okay. So here we will have, that's the major, which we have it as Y. Can I get the center line? No, it's not really at the center. So this will be the minor, which we will call it the Z. Okay, so the clever way of using the orientation of a beam is this way. Orientate the beam, stand it up such that it's like this. Okay, for a beam. Don't slip it down. You slip it down, you are going to get a very small eye. Okay, so to give you a better explanation is this. What is the formula? Of course, the eye section, the formula is not so straightforward. You got to break it into 3 different areas. But if it is a rectangular section, the eye, okay, second moment area, you can calculate as B D power 3 divided by 12. Okay, which is, this is your I major. But if you want to use it flatwise, okay, if you want to use it flatwise, then your B is this, and your D, your D is this, and your B is this. So you see here, in this case, you can easily see mathematically. This I will be your B times by D power 3 divided by 12. So this D here is this D, such a small D. And your B is here. So which one, the pink color or the blue color, is going to give you a bigger eye? The blue one is going to give you a bigger eye. So use it this way. All right, use it this way. Don't slip it down. Okay, Harith, I explained for you. Is it clear now?
Clear, Doctor. Thank you.
Okay, all right. So any other question? No question. Okay. Then yes, Yuling.
So for the section modulus requires, we get 1738. So we find the almost nearer.
Almost nearer. Almost nearby. Must be larger. Then the result of it is that you can see here when you check the moment. When you check the moment, when you check the moment, you get a ratio that is like this. If you get bigger, if you want to get bigger, it's fine. There's no harm. You get bigger, then you're gonna get a ratio that is going to be probably like 0.7, because a bigger section is gonna give you a larger capacity.
Okay. So if we take like we provide WPL equal to 1810, is it okay?
Can, all right, no problem. You will pass.
Okay.
It's
So
just a
just
different
take
size.
nearer lah.
Yes.
Okay. Thank you, Doctor.
Okay. Any other question before we end? Yeah.
For the strength also, we can choose any strength.
Yes, you can choose any one. You are the designer. We have this pen color not nice. We have S275. We have S355. We have S235. So you decide. You buy what you want.
Okay, Atta.
Ya.
Doktor, sebab thickness kita belum tahu lagi kan size benar. So,
Thickness
kita,
nanti bila kita dah pilih soal apa tu? Bila kita dah pilih size tu, kita dah tahu thickness dia. Kita dah tahu dia punya TW. Jadi kita is kind of like chicken and egg lah, mana nak dulu kan. Mula-mula kita dalam fikiran tu kita kata nak kurang daripada 40 mm. Okey, sebab kita kalau lebih daripada 40 mm, dia punya FY nak akan turun. Kalau kita kata nak kurang daripada 40 mm, FY dia akan bersamaan dengan grade, whatever grade that we take, so 275. Maka nanti bila kita pilih size tu, carilah size yang TW-nya ataupun TF-nya kurang daripada 40. Jangan pilih besar sangat.
thickness tu untuk web dan flange lah dua-dua kan.
Yelah, hanya itu saja.
Faham. Banyak nak kena consider.
Banyak.
Kali syarat banyak-banyak kan.
Okay, tak apa, slowly digest. Nak kunyah tu. Slowly.
Doktor, saya ada last question yang pilih UB-UC tu, itu berdasarkan soalan lah. Soalan minta kita
soalan. Sebenarnya okey lah, kita study, yalah sekarang exam lah, sekarang is exam oriented. Tapi jangan study untuk exam oriented je. Study for practice in terms of next time you come out as an engineer. UB-UC dalam exam akan diberi lah whatever, size pun diberi dan kadang-kadang size tak diberi, kadang-kadang size diberi. Tapi dalam hakikat sebenar di practice, okay, reinforced concrete sometimes the architect can give you the size, okay, but when you have a drawing, architect when it comes to steel, dia tak boleh design, dia akan tulis to engineer specification. Okay, so that's where engineers have to do the design. You decide what's you want to use a section of UB or you want to use a section of UC, you decide. But when it comes to a beam, okay, we always want to have it in a rectangular edgewise. Ianya lebih kuat daripada kita letak dia tidur ataupun rendah. Kalau dia rendah, okay, contohnya rendah is UC lah. UC segi 4 in terms of the breadth and depth. Okay, so it may not be clever, tidak berapa bijak lah kalau guna UC untuk beam. Tapi tak salah, boleh. Okay, so the better way is guna UB or RHS. Okay. Nanti sampai kolom bab kolom nanti you kena fikirkan, okay, kolom tu if it is a floor plan, okay, your floor plan, do we put the column nak letak kolom macam ini ke ataupun nak letak kolom macam ini, mana lebih elok? Itu nanti sampai bab kolom nanti you fikirkan, tanyalah. Ada sebab-sebabnya tertentulah. Bukan suka-suka letak aje.
Jadi doktor, jenis-jenis tu semua berdasarkan situasi lah. Kita boleh
situasi, yes.
Boleh pilih je mana-mana.
Betul, situasi dan sebab kenapa.
Okay.
Because in civil engineering is a life of problem and solution. Sometimes may not be so direct. So tengok case by case. Okay. Okay. I stop presenting. I think we can call it a day. So nanti afterwards, what we gonna do, I will communicate in the WhatsApp to confirm whether Khamis pukul 5 kita buat quiz secara ramai-ramai. Okay, that means you don't have no Google Meet, but you just go and do it. There's a time limit. Okay, there's a time limit. You start and you stop. Okay, you miss the boat, you miss the boat. Okay.
Okay, Doctor.
All right, we stop here. Thank you very